Welcome to this video on the concept of stress. It is one of several videos in a short course on stress in structural analysis posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and material relevant for this course. If you are familiar with structural analysis, you will know that the concept of stress is omnipresent in mechanics. The calculation of stress and stress resultants is a central task for an engineer who wants to check that a structural design is safe. With that background, it may surprise you that the concept of stress is quite recent. When Galileo developed the field of strength of materials in 1638, he did not use the concept of stress that we use today. Even the Euler-Bernoulli beam theory, which is fundamental in modern structural analysis, which was invented in 1750, did not employ stress. Although it took another 100 years before the Euler-Bernoulli beam theory gained widespread popularity, it is still noteworthy that it was only with Augustin Cauchy's work in 1822 that the concept of stress on rigid infinitesimally small bodies was developed. Competing theories at the time considered molecular forces instead. Augustin Cauchy considered equilibrium for a tetrahedron like this when he introduced stress in 1822. Stress is often denoted by the Greek symbol sigma. The next slide gives one view of how the concept of stress is used in beam theory today. The sigma symbol is visible in the lower left corner. On the left-hand side are equilibrium equations that link the externally applied load, Q, with the bending moment, M, which is a resultant of the axial stress, sigma. One reason why the concept of stress is helpful is that it allows us to formulate a material law, which relates the stress at every infinitesimally small element inside the beam to the strain there, namely the deformation at that point in the material. Hooke's law, which postulates that the stress is proportional to the strain, is one option for the material law. On the right-hand side of this slide is a kinematic compatibility equation that relates the strain at a point in the material to the deflection of the beam. In this way, we are able to establish a relationship between the load, Q, that is applied to the beam, and the deflection, W, at any point along the beam, using the material behavior at every point inside the material that the beam is made up of. Notice this path from load to deflection via equilibrium, material law, and kinematic compatibility. These ingredients appear in all problems in solid mechanics. The only exception is statically determinate structures, for which equilibrium is sufficient. The next slide introduces the manner in which stress is expressed. Stress is essentially force per unit area. When we spread this point force over the area, then we obtain a stress value. For that reason, stress is expressed in the unit of force over area. Newton per square meter, which is Pascal, is one typical unit for stress. Another popular unit for stress is Newton per square millimeter, which is megapascal. At this point, you may ask if that nicely distributed stress actually exists inside the material. The picture on the next slide suggests that it is a reasonable question. Many materials, such as timber and concrete, have a sort of granularity that makes it difficult to imagine a nice, smooth, uniform distribution of stress inside the material. Although that is easier to imagine for steel, such as these rebars and steel columns, it is fair to ask whether the continuum model that underpins the concept of stress is useful. The answer is that it is most definitely useful, for several reasons. First, the concept of stress opens up to the possibility of establishing mathematical equations for equilibrium, material law, and kinematic compatibility. Second, the concept of stress expresses an average of the forces that act inside small portions of a material. That last point is better understood on the next slide, where stress resultants inside a beam are visualized. These resultants of axial and shear stress are expressions of average stress. More precisely, they represent the integration of stress on infinitesimally small portions of the material over the entire beam cross-section. These stress resultants, including bending moment, shear force, and axial force, appear in capacity formulas in every design standard for various materials. In other words, the structural engineer usually employ resultants of stress over the cross-section to check that the capacity of the structure is sufficient. This is why it is important in structural analysis to learn how to draw bending moment diagrams, shear force diagrams, and axial force diagrams. It is all based on the concept of stress, which expresses the average of forces inside materials that in reality may be more discontinuous. The next slide gives typical stress values for steel, concrete, and wood. Because strain is a dimensionless quantity, often expressed as deformed length divided by original length, the material stiffness, E, has the same unit as the stress. The table shows that the capacity of steel to carry stress is the highest of these materials. It can reach a stress of 350 megapascal or more before it breaks. The strength of concrete may be 30 megapascal or more. The strength of wood may be around 15 megapascal, depending on the species of wood and the direction of loading. Typical values for the stiffness of the material, sometimes referred to as Young's modulus, are shown in the middle column of this table. The previous slides have focused on axial stress. This slide introduces shear stress. It is often denoted by the Greek symbol tau, although sigma is sometimes used for shear stress as well. You can see that the concept of shear stress is similar to that of axial stress. Both types of stresses can be interpreted as force spread over an area, but shear stresses are acting parallel with that area, while we saw that axial stresses act perpendicular to the area. This final slide further develops the notation for stress. We call the stresses that act along the coordinate axes coordinate stresses. Notice that all these gray shaded portions of material are infinitesimally small. Also notice that the stress symbols often have subscripts to tell in which direction they act. More precisely, the first index of a stress gives the direction of the surface normal of the surface it acts, while the second index tells the direction of the stress itself. The notation shown in this slide gives the foundation for the practical use of the concept of stress to establish equilibrium, material laws, etc. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and material relevant for the modern structural engineer. See you soon.